In this video, let's review the most important concept in this three chapters: probability, discrete distribution, and continuous distribution, to understand the foundation of inferential statistics. In probability, we studied that probability is a measurement of the likelihood that one outcome occurs. But how can we do that? By counting. We count the number of all possible outcomes and the number of ways that the event E can occur. Then we measure the probability using this ratio, this proportion, or a percentage that we obtain from this quotient. In the empirical approach, we can approximate the probability counting the number of ways that the event E occur when we repeat the procedure and divided by the total number of trials. In a discrete distribution, the random variable x can take a finite number of values, and we can do the procedure and we can count the number of times that each value appears, and after that we can obtain the relative frequency, and we can use this relative frequency to approach probability. We can graph all values that this discrete random variable can take and plot the number of ways that each value occurs. We can use points like this, one above the other, where each point represents one occurrence of the corresponding value. Also, we can use bar to do this graph, and each bar could be obtained from little block where each block represents one observation. Using this graph or this table, we can compute relative frequency, or we can approach probability of each value by counting the number of times that each value appear. If we graph either the absolute frequency or the relative frequency, we will obtain approximately the same shape. To compute the probability that this random variable take this value or one value below, we need to count all of these observations and divide it by the total. We use this formula to compute probability using absolute frequency. If we want to use this graph, we need to obtain the probability for each of these values of the random variable, and we must add its corresponding probability. In a binomial distribution, we have a formula to obtain the probability of one value, and that is the formula for a binomial distribution, where P is the probability of success and Q is the probability of failure, and N is the number of trials and X is the number of success that we want that this event occur. Then in those cases, we need to compute the probability of each of these values, and we need to add all of these probability using this formula for each one. Let's explain how can we compute probability when the random variable is continuous. Suppose that this is a population which consists of items. These items could be people, merchandise, paper, or event. And we want to study one characteristic in this population. We are going to name this characteristic by X. We can measure this characteristic in all members of the population, then we can obtain the census. This is the census. And suppose that this is the minimum value that this characteristic contains, and this could be the maximum value, and the characteristics can take continuously all value between these 2 points. Then for each point of this population, we have one measurement here. We can organize all of these points in this graph according its measurement. We plot the first point, suppose here, and this is the measurement. And suppose that this measurement appear here again and correspond to this individual. Then we plot this individual here, and so on. Then when we organize all of these points in this number line, it's possible that we will obtain something like this. This is a mound-shaped distribution, like a normal distribution. Observe that the most popular value in this data must be in the center of this pile. In a normal distribution, this value will be the mean, the center of this pile. We can use this curve to represent this distribution. Mathematicians found that the equation of this curve is given by this formula, where E is 2.718182, pi is 3.1415, mu is the mean of the population, and sigma is the standard deviation of the population that in this graph could be approximately this quantity. 3 standard deviation to the left and 3 standard deviation to the right must reach these 2 points. Between these 2 points we have approximately 99.7% of all measurements. Then how can we compute the probability that this random variable can take this value or one value below to this value? We need to count. We need to count all items of the population that have this measurement and all items that have a measurement below this value. And after that, we need to divide by the total member of the population, the total points. But a statistician, instead of counting points, they measure area. A statistician state that 100% of all points are under this score. In other words, they state that the area under this score should be equal 1. Remember that 100% is equivalent to 1, and the probability is a number between 0 when it's impossible and 1 which is certain. Mathematicians compute the probability that the random variable x is equal to x sub 0 or smaller than this, computing the integral of this function from negative infinity to x sub 0, the integral of this function. Also, they can compute the probability that the random variable x take a value between x sub 0 and x sub 1 doing this integral. Between x sub 0 to x sub 1, then they obtain the area under the curve between x sub 0 and x sub 1. That is the area, and we divided this area by 1, and that is the probability that this random variable take a value between x sub 0 and x sub 1. Because this operation is a little complicated, they do the following procedure to compute probability of a normal distribution. Since the shape of the normal distribution depends on where is located the center mu and the standard deviation sigma, which is this distance, then this shape could have different form. Could be narrower like this or flat like this. On the other hand, if we want to find the z-score of this measurement, we have to use this formula: x minus the mean divided by the standard deviation. Remember, the z-score is the number of standard deviation that this value is from the mean. The z-score could be positive when x is on the right and could be negative when x is on the left of the mean. For example, the z-score of this value is 2 standard deviation. In this case, the z-score for this value is equal to. The z-score for this other value will be negative 3. In this other distribution, the z-score of this value is equal 1. The z-score of this value is equal to. The z-score of this value is equal negative 2. And we can do the same for this curve. Remember, under this curve we have 100% of all points, all items, and we can organize all of these points using instead x the corresponding z-score for each point. For example, the z-score of all points located exactly here in the center, the z-score when x is equal to the mean, we need to subtract this value, which is the mean minus the mean over the standard deviation. This value will be 0. Then the z-score of all of these points are 0. Then we plot all of this value here when we use this scale. Z-score, all of these points will be located here, all of these points. The z-score of all points located here, 2 standard deviation, this point that is 2 standard deviation to the left, then all of these points are located, the z-score of all of these points is 2, and when we can plot all of these points in this graph here, when this is negative 1, negative 2, then all of these points will be plotted in this way. Then we can do the same thing for all of these points, and we obtain this graph. This is the standard normal distribution. If we organize all points under this distribution according to the z-score, we will obtain the same curve, and the same thing occurs for this distribution. Then we can transform any normal distribution in the standard normal distribution. In this distribution, the mean is 0 and the standard deviation is equal 1. All of these scores fulfill the empirical rule, which states the area between one standard deviation represents 68% of the total area. In other words, 68% of the population have a z-score between -1 and 1. 95% of the population have a z-score between -2 and 2. And 99.7% of the population have a z-score between -3 and 3 standard deviation. If we want to find the probability that this random variable is between this value and this value, we need to compute this area, and this area is equivalent in the standard normal distribution to this area. Compute the area is easier in the standard normal distribution. We can transform any normal distribution in the standard normal distribution using this transformation, using z-score. Statisticians summarize the area under this curve in tables. The most popular tables are the negative and the positive z-score table. In both tables, they compute probability to the left. In this table, we have the area of all values located to the right of the mean, and we start in 0, 0, 0, 1, 0, 2 until 3.4. The area to the left of point of 0 is 50%, then must appear in the table with 4 decimal 0.500. This area is 0.5000. In this row appear the second decimal of the z-score from 0, 0, 0, 0, 0, 0, 1, 0, 0, 2 until 0, 9. The second decimal. The area to the left, this point 3.49, in the table appear that is 0.9998. Almost 100% of all value have a z-score below 3.49. Then in the negative z-score table, we have the area to the left for all values that are located to the left of the mean. And in this table, we start with this point that is located 3.49 standard deviation to the left of the mean. The area to the left appear in this corner, which is 0.0002. This area is 0.002 and correspond to this z-score 3.4, and the second decimal is 9. And this table finish here in 0. And in this table we have negative 3.4 here, negative 3.3 here, negative 3.2 here, until negative 0.00. Then this will be 000, and this area to the left of 0 exactly must be 0.500. 50% of the value are located to the left of the mean. Some statisticians use only one table because the normal distribution is symmetric. In this table we can find the area between 0 and a positive z-score, and in this column appear the z-score from 0.0, 0.1 until 3.0, and in this row the second decimal of the z-score 0.001, 0.2 until 0.9. Then the area from 0 to 0 is 0.0000, and the area from 0 to 3.0 is 0.4990. Is exactly this area. This table gives me the area to the left of 3.0, then should be this area to the left. Then this area is equal this area, which is 0.4990 plus this other one that is 0.50. Then in this table, in 3.09, we have this one plus 0.50. Then should be 0.9990 that is obtained from this value plus 0.50, which is 0.9990. That is the relationship between this table and this other table. We can use this table in two different ways. Given a z-score, we want to find the area to the left, then we need to find 1.6 in this column and the second decimal 0.05 in this row. Then in this intersection, we will 0.9505. This number represents probability to the left of this point in the positive C-score table. That means that the probability to the left of one point located 1.65 standard deviation from the center, this area is 0.9505, or you can interpret it this way: 95.05% of all value have a C-score below 1.65. Also, you can find probability to the right subtracting this area from 1. Then this area is exactly this one. This area is 0.095, could be rounded 0.05. It means that 5% of the population have a C-score above 1.65. These are the type 1 problem. Given a value, given a C-score, we need to find probability either to the right or to the left. Then the type 2 problem is the inverse case. Given the probability either to the right or to the left, we need to find the corresponding C-score or the value. For example, is given this probability to the right, we need to find this value such that 4.95% of the value are above this number. Since this table works with probability to the left, we need to find the probability to the left of this point, subtracting this area from 1, that is equal 0.9505. Then if this probability is 0.9505, we need to find this corresponding C-score. We need to go to the table and we need to find this area in the main body of the table. Then after that, we need to obtain the corresponding C-score. Then the C-score of this value is 1.65. It's located 1.65 standard deviation to the right of the center of the mean. Then if this value is located to the 1.65 standard deviation to the right of the mean, this value should be equal the mean plus the C-score times the standard deviation. Then if the mean is given and the standard deviation is given, you can find this value such that the 4.95% of the value are above this number.